Good morning, and welcome to this 10th edition of Great Designs in Steel technical webinars. My name is Brian Esterberg, and I'm the Senior Automotive Market Strategist at the American Iron and Steel Institute. Today's presentation is Considerations for Design and Stamping of Generation 3 Steel Grades. And we're going to give folks just a moment to join the webinar. I see a number of people still entering. If you've not done so, the website is now available to register for Great Designs in Steel. The Great Designs in Steel Annual Symposium takes place May 20th in Novi, Michigan. We'll be returning to the same venue, which now has a new name, the Vibe Credit Union Showplace in Novi, Michigan. A preview of our agenda will be released next week, but you don't need to wait. You can register now at greatdesignsinsteel.com. It's now my pleasure to welcome our speakers, Alexandre Cortez, lead engineer at ArcelorMittal USA, joined by Cheng Zeng, research and development manager at KIRCHHOFF Automotive North America, and their presentation is titled Considerations for Design and Stamping of Generation 3 Steel Grades. Alex and Cheng, good morning and welcome. I'll give you the screen.
Morning.
Good morning, everyone. Yep. So, good morning, everyone. I hope that you can see my screen.
We do.
Okay. Thanks for joining for GDIS webinar on stamping of Gen 3 steel grades. I am Alexandre Cortez from ArcelorMittal North America R&D. Today we will focus on how to stamp Gen 3 steels successfully and what to watch in production. And let me start with the roadmap. Here is the flow of, I will give you an introduction of ArcelorMittal, followed by product offering and the terminology. And then we review the Gen 3 steels and do general consideration for stamping advanced high-strength steel. And then Cheng will introduce the real case at Kirchhoff with showing the forming and the welding development and the 11.8 B pillar production implementation. And then I back with a stamping and design guidelines followed by welding and the conclusion. So let's introduce first the ArcelorMittal. ArcelorMittal is a global steel and mining leader, about 125,000 employees in 60 countries. We lead in major steel markets, including automotive, supported by strong R&D and the technology capabilities. With primary steel making in 15 countries, we are positioned across mature and also emerging markets. Our main focus is smart steel for people and planet. This is just to give a global R&D presence. We are placed in 90 countries with 14 geographical sites, including research centers, R&D units, product and process deployment centers, co-engineering. In North America, we active in East Chicago and Southfield and Hamilton, Canada. And also we have a major European sites and coverage in Asia, including Tokyo. Next, I will frame how our auto R&D translating to deployable steel solutions. We have an in-house S-in-Motion project. This is a set of generic steel solutions developed by ArcelorMittal, showing optimized steel grades, design and process, a solution that meets the major technical requirements and constraints, and also numerically validate solutions. It covers not only ICE body models, but also the electrification of the vehicles. And we have a set of solutions using our steel portfolio. It's helping OEMs to meet their challenges with our best-in-class products and applications, opening collaborations opportunities to support OEMs on advanced engineering and the vehicle programs. With that context, let's align our product offering and the terminology. ArcelorMittal has a wide set of automotive grades in production today, from conventional grades to advanced high-strength steel and ultra-high-strength steel. I would like to highlight Fortform HF. This is a third generation for cold stamping grade. And also we have a UZ board and duct board for hot stamping. This is our brand names for press hardenable steel. And we have a strength level with this kind of grades up to 2000 megapascal. And also we have a martensite MP grades. This is a cold rolled martensite MP steel designed to be used with a hole forming process. We have a strength level currently from 1300 to 1500 MPI. Also, we have a wide advanced high strength steel family grades, including dual phase, multi-phase, and the complex phase steel families from 500 to 11.8 MPI. At least, and in the end, we have a standard conventional offering also mild HSLA grades, IF and BH. So what makes Gen 3 special versus early generation? This is our portfolio spread in elongation and tensile strength graph. As you can see, as far as we increase the strength of the steel, the elongation reduce. It is more hard for stamping point of view. Our Gen 3 product is located here in this portion of the graph, and it's bringing higher formability at equivalent strength compared with the first gen of DP grades, and high big hardenability combined with significant working hardening. It results in significant yield strength increase after forming and improve part performance, enabling lightweight structural components using cold stamping and the hole forming process. This is the same graph, but just to highlight the comparison between the first generation of DP family compared with the third gen, the potential we have between 10% to 50% weight reduction compared with the Gen 3 steel grades. We have two type of grades. HF is our uncoated version that cover 9.8 and 11.8 strength level, and also our Fortform brand name 9.8 and 11.8. This is a GI version. Okay, so next I will briefly explain the KMP concept behind the Gen 3 microstructure. Gen 3 commonly uses the quenching and partitioning process. This is a typical thermal processing that includes 4 phases. The first one is soaking that determines the initial microstructure. Basically, we have austenite grains formed during soaking. And then we have the second phase quenching. This is a partial transformation of austenite to martensite. And in this phase, we have a martensite lefts formed during quench. And then we increase a little bit the temperature for the third phase, partitioning. This is a competition between carbon partitioning from martensite to austenite. In this phase, carbon partitioning from martensite to untransformed austenite and bainite at partitioning phase. And then finally, in the fourth phase, we have the final cooling. This is where formation of retained austenite and the fresh martensite happen. And we have basically carbon saturated austenite remains stable in the final cooling with a high temperate martensite and bainite. This brings for the steel the high formability, very good ductility and forming behavior, high bake hard index, and a good global formability compared with the first generation of DP grades. These are our global availability. And as you can see in North America, we have these different coatings for 3rd gen products, including 9.8 and 11.8 strength level. And in Europe, we have one more grade, 1050, that it's include also a different coating, electrogalvanized and jet-gal. With that foundation, let's shift to stamping, starting with general advanced high-strength steel realities. And I would like to highlight some considerations for stamping. Advanced high-strength steel is stampable, but not business as usual. Higher strength amplifies processes sensitive. Spring back is inherent of this kind of grades. Strength path strongly influences the failure limits. Edge quality is critical. Blanking and the trimming conditions directly affect the edge cracking risk. Local formability often governs part feasibility, and the global versus local formability must be distinguished. Okay. I would like also to highlight enablers for robust advanced high-strength steel stamping. First, process robustness, stable binder force and the draw bead control, plus well-defined and a repeatable process window. As you can see here in the graph, this is an example of 4 different processes generate different levels of elastic stress. And tooling press, higher pressure demand correct to materials and surface quality. Press stiffness and cushion control affects repeatability. And lubrication and friction control. Advanced high-strength steel is friction sensitive, so consistent lubricant selection and application are essential. And CAE supports feasibility, and the spring back trends to edge local failures need special attention. Now I would like to invite Cheng to present the KIRCHHOFF real case with Gen 3 steel forming and welding development and the 11.8 B pillar production implementation. Cheng, welcome, and the floor is yours.
Okay. Thank you for the nice introduction offline and as well as the great presentation from the Alex. Okay, I will share my screen. Okay, my topic will be cover the KIRCHHOFF Automotive Gen 3 steels forming and welding development successful journey, as well as the 1180 B production implementation. Okay, first I will start with the introduction, one slide, and then we'll be talking about 980, 1180 forming, and then the welding of 980, 1180, and then the 1180 B production implementation, and finally conclude with the acknowledgement. Okay, who we are. KIRCHHOFF Automotive is a development partner for the automotive industry, for the complex metal and hybrid structure for the body in white and chassis. We offer the body solution for automotive to make a mobility safe with innovative and economical lightweight product. In the 2024, in North America, that's 15.5 million passenger and light commercial vehicle produced. 58% of them contain at least one of our parts in North America. Currently, globally, we have the 30 plants and 9 sales office, as well as the close to 8,000 employees. Okay. For Gen 3 steels development, we start from 2019, end of 2019, Q4. You can see here, we starting from material characterizations, and then we pick up a parts to do the demo parts design, and then we build a tool to validate the simulations as well as the dimension control, and at the same time we do the welding and then circle grid analysis, strain analysis, and as well as the full B-plate simulation and to simulate the tonnages as well as the stress concentration area, find out where it could be potentially have a issue in future production. And in 2021, second quarter, we were awarded the first North America's 1180 B-plate business with two-piece design, very innovative. And that one will help us the tonnage control. And we launched it successfully in the second quarter of 2023. Okay, I will get to a few more details on these couple steps. First, it's experimental path design and the forming trial. This is the first path we have evaluated in-house to do the geometry steels forming analysis. As you can see here, we pick out the lower portion of our sample parts. And then we are changing the radius and to make it more friendly for the future spot welding. And also we create a through hole here and with adjustable punch for the down geometry creation in order for us to stretch the materials as much as we can to see what kind of the design limit will be in future product design. So this is a few features here you see here, watch radius as well as the nose. Okay, so when we did the simulation, you will see the next slide here. We did a simulation and you will see those hot spots, which are stress concentration area. And that's exactly what we intend to do. Try to evaluate what would be the minimum radius could be and what kind of materials can be stretched out. We did the forming simulations and we highlight a few hot spots, and then we do the tool build and trial. And you can see here correlated very well, cracking exactly at the location we predict during this forming simulation. We did it in the AutoForm in-house as well as the tool shop at the Dynaform simulation. They correlate very closely, and this is the first hit, and that's tool build, and that's the first stamping process we did during pandemic and 2020. Okay, and then in-house we also bring it to the servo press for different parameter trials under the different dwell time and the parameters to check the forming characteristic as well as the materials flow. Okay, we incremental 10 millimeters here, and then we see where is the material could go. And you can see here, this is first and then 20, 30, and 40s. Okay, and this is a significant improvement. You see here, we're changing from original from the square blank to the with big radius, which help the stress concentrations mitigations. And then tonnage also read out a very well matched the forming simulation. That build up a very good confidence for us to using in future production. Also, we did the so-called grid analysis as trends analysis, try to see where could be the materials deformation start, as well as what could be the future hotspot areas and the formability look like where materials goes. And then we improve the our tools with a field of the location. You see some we have drop our angles change, some we overbend in order to get the dimension under the spec, and some we add in some material in order to bring the wall to the nominal. Okay, and also the flanges, geometry, small changes in order to get dimension to the spec. Okay. In terms of welding, we did a lot of welding study. You can see from here, we did spot welding, we did projection welding, and we did MIG welding, laser welding, and laser MIG hybrid welding for these materials. We have done a lot of study on this and launched lots of successful laser welding product in our production. So we have all the tools we need. So when we start with this material, we did most of the study as need. Okay, so this you can see here, this is the spot welding samples. We weld over 300 samples in order to get the different geometry tips, different material, different combinations. And then we did the analysis on the pull tensile test, color tension test. You will see in the next slide. Then others, we did MIG welding samples. And then we did laser welding samples. Okay, and we did a hybrid welding sample as well as the edge welding samples. For one of the most production to get ready for production. Spot welding is our key focus. As you can see here, we start in the spot welding with the 980 and 1180 under different combination, coated and uncoated materials. One other concern is zinc coated steel, the welding LME concern. And that's why we did a lot of study, follow a similar methodology as shown here. See here, we did the chisel test, coupon test, and they're under different parameters. And then we do the claw tension test, try to find out any kind of the welding LME into the interfacial. As long as you have a cracking in the interfacial, then you basically pull it will immediately crack, and then you will see the curve is significantly different. Okay, and then you can see here we also did weld surface inspections, and then also interfacial inspections. And the most one of the items we focus is 1180 uncoated steel and the 420 980 materials, which we weld for production, target for our production. All the weld samples showing here after certain development, we put very good nuggets with a wide range of welding parameters, as well as the impulse welding, direct welding, both work well without LV crack seam. Okay. In terms of production implementation, you can see here, this is the first one we want, 1180B per production. Basically, we got the strategic partnership with ArcelorMittal, or co-founder Gen 3, 1180 and 980 coupons for our trials and prototype, as well as the production. And then also we did the strategic partnership with OEM on these two innovative 2P design. You can see here we launched successfully into the vehicle, 3 vehicles from General Motors, Chevrolet Traverse, Buick, Enclave, and also CMC Cadillac. Okay, with close to 400K annual volume. So high strength ductility stiffness was designed into the parts where it's needed, and the uppers uncoated gently steel 1180 welds lower coated steel with our optimized welding parameter to avoid some kind of a corrosion concern. Also maintain the crush performance as needed. Total mass is 6.5 kilos. And then the robotic spot welding, the 48 spot welding projection, 2 nut on the gentry, and then a few others on the other material. So in terms of production implementations, tool development for forming and welding, I listed a few sections here. Unfortunately, I cannot show the whole picture of the die, but this one gives you a quick snapshot of what it is look like. The tool was built completely in-house by our KIRCHHOFF Poland die shop. They do simulation and build the tools with several stations, and plus tonnages match very well with the simulation. And we also with the decoiler to resolve some of high strength, high spin back coil set, and stamping tools launched successfully without any adjustment when we hitting the whole line running, first in July 2023. And then the welding tool also successfully launched. You can see here these blanking die run samples, and this is forming die running samples, and this is the welding cells, as well as the projection welding, spot welding and projection welding, robotic. Okay. So in terms of I would like to highlight the home line's running forming state results. KIRCHHOFF in-house smart forming tools design, and for dimension control, and tool built with well-established forming simulation for high strength steel and spin back control compensation method. Through a few recuts, achieve the 90% of PIST percentage inspection point that is satisfied tolerance. Okay, SPC point measurements also very nice in the whole line. It's within negatively 0.245 and plus the 0.3 millimeters. Mostly it's within plus minus 0.2. And this is the bottom simulation result, and the top showing you the full B plus, as well as some quality check. Okay. The spec from OEM, they have a wide range of spec. You can see here the yield strength from OEM, it's 850 to 1125 MPa, and ArcelorMittal, our material supplier partner, and it's 850 and 1060. We do receive some the different coil at different spec, and we have run successfully through our line since SOP. Okay. For the welding side, there's two key items. One is resist spot welding, and one is the projection welding. Both have been developed successfully and optimized to achieve the consistent welding nugget size. And we got the sputter expulsion free with the optimized welding parameters. You can see here some spot welding on the geometry to the lower the zinc-coated steels, and the projection welding both teardowns showing good nuggets and consistent meet OEM specs. We also have welding monitor software to analyze the welding results and graphing. Okay, so the project has been running very successfully. I will take this opportunity to thank you for several partnership. One is the Gentry Steels support partnership from a few of our suppliers. Mainly, I think it's the ArcelorMittal for the trials prototype, as well as a few competitors we also evaluate as well. And the OEM customer design for this innovative deeper design and new business award opportunity. And also thank you for our executive team for the leadership and the project operation team for the development and production launch. Last but not least, it's the Great Design Steel for hosting this great seminar. Okay, thank you. We did publish a couple of news through LinkedIn as well as the K Mobiles and K Nets. Okay, let's cover some key topics from my end. Thank you. I'll open for the questions at the end of the presentation. Thank you.
Okay, thank you, Cheng. Okay. So, yeah, let's return now. We shift from general advanced high strength steel principles to Gen 3. And let's anchor first on typical mechanical properties and why they matter. This is our grades that we have here in North America. And with the typical tensile, typical mechanical properties that cover a range from 980 to 1180 MPI. Why properties matter? Higher yield strength and tensile strength, higher forming loads and the spring back risk. Geometry compensation becomes critical. Total elongation increased global formability as well. Holy expansion, edge stretch capability, driver string quality, clearance, and edge strain limits. And with that, let's talk about edge formability. Out of plane shear, the issue that we can found is edge tearing splits associated with out of plane shear, especially when the material buckles instead of conforming to the flange radius. As a root cause, ETL applies to in-plane tension, out of plane shear. It is a different failure mode, poor support during flange leads to buckling and shear. As a mitigation, designing flanges operation to avoid out of plane, provides proper support of sheet during flanging, and validate tool head and support surfaces in tryout. Another edge formability concern is the cutting clearance and the cut edge quality, and trim bypass notch. The issue is premature edge fracture, splits during flanging or stretch flanging. Edge failures below expected the ETL. And as root cause, production edges are worse than lab hair specimens. Blur visible edge damage, poor shear edge condition, incorrect or inconsistent cutting clearance, delay between blanking, trimming, and the forming reduces the cut edge formability. As a mitigation solution, maintain cutting steel conditions to eliminate burrs and the damage. Keep clearance consistent between 12 to 22% clearance of thickness. Use safety factors, but don't rely on them for severe edges, and form with minimal delay after cutting. Now let's move from edges to bending failures, especially bend and bend under tension. The issue that you can find is cracks on bend radius or straight side walls after bend and bend. Minimal necking, stress risers on bend strengthened surfaces like, for example, numbered stamps or sharp features. The root cause, low correlation between radius and thickness combined with sidewall tension thinning, detrimental strain path, and stress risers on the surface that later goes into tension. As a mitigation, use a good correlation RNT. We recommend 5 and above as a guideline for bending under tension, and reduce sidewall tension thinning where possible, process and addendum turning, and avoid placing stamp marks in high movement areas. And for multiple forming operations, the issue we raise is split occurs below standard FLC curve. Edge split not predicted by simulation in reform operations. And as a root cause, nonlinear strain path reduce failure strain below the FLC. Compression and tension path is especially harmful for advanced high-strength steel and third-gen products. Limited secondary forming capacity for this kind of grades. Press strains reduce allowable ETL in later edge stretching after trimming. As a mitigation solution, when possible, do all required forming in just one operation. If secondary forming is needed, only forms with minimal first operation strain. Establish length of line in first operation, and avoid post-trim edge stretching. Treat edge strain as one and done. Finally, in stamp, concerning about the wrinkles and the spring back and the lubrication. Wrinkles, the issue can be raised as zones that can translate to splits, edge fracture, fold over, trimming problems. The root cause, uncontrolled flow, sudden restriction as wrinkly iron out. And as a mitigation, use draw beads plus correct binders, spotting to control the flow. Allow clearance for thickening, avoid the wrinkles at the trim line, and don't put blank edge to draw beads. Related to spring back management, the issue that we raise is dimension deviation after form. Spring back can increase with part complexity. The root cause, higher elastic stress at 9.8 and 11.8 and beyond the strength level. Compensation changes bead and binder geometry and can change formability. The mitigation applies suitable compensation, stamping techniques, plus geometry features, rerun fair after compensation to confirm feasibility. And the last one, heat generation and the lubrication. Higher stamping heat when using Gen 3, add the formability at a high strength. The root cause, a higher strain level versus first and second generation of steel grades. The mitigation selected the lubricant that performs at a higher temperature, handle parts accordingly, and maintain consistent lubrication and the friction control for robustness. Next section, we will cover the design guidelines and where third gen fits best. I would like to propose here the development rationale for forming spring back sensitive parts like third gen products from design to tooling phase. When we think about to design parts, we need to integrate steel part design flow, considering the design, the vehicle and system requirement, concept, geometry and section strategy, material strategy, stamping, feasibility and die process, joining, welding, and the strategy. And then we will have design and release it, and the manufacturing robustness with a good part and a good process. But I would like to highlight here that these steps is correlated to each other, like joining, welding strategy is correlated with vehicle and system requirements, material strategy and the stamping feasibility die process. I would like to highlight this two topics, two steps here, that when we start to design, we must to add in our concept the stamping process, you know, and then proposing this, we have this kind of methodology in ArcelorMittal, developed by ArcelorMittal R&D. Initial part design, we do evaluation to check the forming and the spring back to the virtual simulations. And then we have initial part design and the first forming process defined. And then we do another step that we can develop tools for spring back analysis and the scatter analysis. And then we implemented the countermeasures on that. And then we have a optimized part design and the process. And then we have tooling adaptation. And then we process with die compensation if needed. And then in the end, we will have a robust part and process. Here, this is an example of this generic methodology developed by ArcelorMittal, taking into account the spring back during the part development stages. This is an A-pillar part with 4411A 1.0. As you can see here, the initial part without any feature implemented in the part yet. And then here we add some implementation in the flange over here, and made this initial spring back simulation, and the spring back is still into the part. And then some changes on the shape modification was done in the sidewall, adding some embossments in the sidewall. And then we made another step of simulation to check the final spring back. It achieved 95% in the accurate in the dimension part. Okay, beyond a single part, here are the typical application areas and the lightweighting potential. I would like to highlight for upper body the A-pillar, B-pillar, roof rail, shotgun, and the A-pillar, and the underbody, tunnel, front rail, ski, seat cross members, and the underbody rail. And then comparing the third gen versus the first generation of DP grades, we have a potential mass saving, keeping the same performance of the baseline material used. Okay, now we will switch to joining welding considerations for Gen 3. First, I would like to highlight the GI 4498 product. Compared with the DP98, weld cross tensile strength is lower and the tensile shear strength is higher. I would like to highlight for this product that the paint baking operation can improve weld CTS, as you can see in the graphic here, without paint baking, and CTS with paint baking over here, with the increase in strength. And here is our showing that we use the pulses and welding good weld size nugget, and also achieve the strength for CTS and TSS. For our micro hardness, we achieve 500 in the nugget area, 500 Vickers. And for GI 4411A 1.5, also you'd like to highlight that wide welding current range can be obtained with standard parameters, and also improved cross tensile strength can be achieved after paint baking. Here, this is the value with after paint baking. And as a micro hardness, we achieve 500 Vickers as well. A related concern, people ask about LME. Regarding LME, this is a methodology developed by ASP for rapid LME testing crack acceptance criteria. In this methodology was defined the 5 types of cracking. The most severe for third gen products is type B, that it's out of electrode imprint, and it's also reduced the fatigue life of the parts. And we use this methodology for test our Fortform GI 11.8, and we applied several type of amperage and no critical concern on LME crack occurrence in this test methodology applied for this grade. You can see more details about this rapid LME test on this website. And then let's wrap up with the key takeaways to close. I will summary that Fortform and HF are Gen 3 steel designed for cold stamping. This steel enable lightweight structural design while maintaining part performance and robustness. ArcelorMittal Gen 3 deliver an optimized balance of performance, manufacturability, and application readiness. Stamping and welding feasibility have been validated, and the grades are available for customer in worldwide basis. And ArcelorMittal provides technical expertise and application support to help customers, and the more technical data available on demand. I invited all of you to explore ArcelorMittal Automotive catalog in North America through this website, and discover also our best-in-class steel solution in our Automotive ArcelorMittal website. I would like to thank you, and I am open for a Q&A session. Okay, thank you so much.
Thank you very much, Alex and Cheng. We'll now go to the questions. Again, as a reminder, if you have a question, please submit it in the Q&A panel. Okay, so first question here is for Cheng. The question is, did KIRCHHOFF experience any splitting or cracking in reality that the simulation did not predict? For instance, splitting starting from the edge of the part.
I would say no. We did a simulation, basically has several ones. One is in AutoFun simulation, and in the tool builds we using the pen stamp simulation in Poland tool shop, and they predict quite well in terms of the crack potential splitting or crack initiation. For Gen 3 steels, for us, we see not so much concern, more on the dimensions, on the a few hotspots of which we need to have get to the perfect dimension control. Yeah. So we cut a few more than normal stamping high strength steel, but in terms of cracking, no. Yeah.
Okay. The second question here seems to be a little bit more on the metallurgy side, and it I think is for you, Alex. Talking about many limitations of third gens coming from local ductility limitations like fracture string, critical bending, radii, etc., and LME sensitivity. Dave Barber is asking, saying decarburization control during annealing can improve these properties. So I guess to what extent is this technique, i.e. decarburization control, can be considered to enhance Gen 3s for usage and implementation?
Yeah, sorry, could you repeat the question, Heshen?
Well, I think it's a more detailed question regarding decarburization of Gen 3s and the relationship between doing that and improving some of the limitations. Do you believe that is something that has been considered?
Oh, yeah, this is could be considered, and of course that the process must to be very well controlled for this kind of grade, like we have the quenching and partitioning thermal process. And of course that if we have implement some decarbonization and other things, it will improve the final microstructure product.
Okay.
Okay.
I think
Thank
that
you.
kind of takes care of that. Another question, and I think, if I'm not mistaken, Alex, you already mentioned that, or at least answered that, but it's again for Cheng. And the question is, do you happen to know what percentage of trim clearance yielded the best quality mechanically sheared edge? 5, 10, 15%. I think, Alex, you had mentioned some of the best practices between 12 and 22%, if I'm not mistaken, if I recall. But Cheng, can you comment
Yes.
on that?
Yeah, I can comment on that. Yeah, we do because this is the high strength steels does bring some more tool wear, especially on the trimming element side. From our best practice, based on the last 2 years of production running, we feel that 15% is one of the ideal. Yeah.
Okay, good. One more question for Cheng. KIRCHHOFF's forming simulations modeled global formability areas very well. So were there areas on your part that required more local formability? And how do you predict material limits in areas of local formability?
That's a very good question. Yeah, we basically, when we do the materials forming simulations, we do the try to do the overall look like, and to make sure the assembly meeting the GD&T key dimensions. But for some localized, definitely is one of the items we need to look at, because it could be associated to the future potential splitting if that's too many materials. So part design need to be a little bit smarter in order to get the material flow more naturally and more smoothly. And for some stress concentration areas, definitely we may modify the tool, adding like a 980 tools we demonstrate tool. We add in some material to bring the walls out a little bit in order to make the geometries fit. So yeah, definitely the localized, definitely hotspot area always needed to watch, because that's the potential splitting area, and that one we need to look into, like radial design, or maybe adding some beads there to allow for material to flow, or spring back control. So that's quite some useful technique our floor team have built up. Thank you.
Understood. Yeah, absolutely. Question here. Could you clarify if there have been any applications involving welded, coated Gen 3 parts? I'm not quite sure where this one is leading, but it might be related to LME. But anyway, this may be either Cheng or Alex. If Alex, you want to field that first?
Yeah. So yeah, we have used the developed method based on ASCP HAP LME methodology, and we tested our products on that, and we not find any concern about LME. But of course, that depends of the parameters that we have in shop floor. We must to adapt the welding parameters and to do some trials with different stack ups to find the best condition for each case. This is specific for each customer, but we have a technical team that can support on that if needed. Okay.
Very good.
Yeah, maybe I can comment one more thing. Is I personally did most of the welding combination in 2T and 3T. Even the most challenging one, and it's Gen 3, and then we put a thin gauge outside. That one was challenged by one of the OEM asked me to do. I think for the very challenging one, you may see the welding parameters a little bit narrow, but it can be done. From our welding 2T, so we even the coating materials, we don't see the LME concern. Yeah. on the small body.
Yep.
Next question question is the gentleman would like some clarification for delay between cutting and forming for edge cracks.
Yeah. Okay. Yeah, this is was based on our technical experience to the third gen material application at customers, and yeah, we recommend that when we cutting the edge, we must to have a delay, and also more technical details. My team can the question can be addressed to them, and then we can answer in appropriate way.
Okay.
Thank you.
And I'd like to remind our participants, if we don't get to your question, please feel free to reach out to Alex or Cheng at the emails shown on the screen for further clarification, because I see we're getting a lot of questions actually, which is really good. So another one is in regards to hoop strain, and assuming the quality of the edge is even more critical, what is the criteria of trimmed edge cut quality have you seen on the blank? I think it's related to the first question. How often is maintenance required in the trimmed edge of the blank where hoop strain is prevalent? So again, it's really the edge quality. So can you comment on how often do we need to maintain the cutting tool?
Yeah, I think that Cheng, can you take this question based on the experience that you faced in Kirchhoff?
Yeah, I think right now we do have the see some challenges, the trimming edges as you find out. The frequency right now, last time we struck roughly about say 2 shift. Right now we shift the sun hotspot areas. We depends on the materials, the material trim die material you are using. Last time at the beginning of launch, I heard they need retrim after roughly about 5,000 pass dampings, and then looking into a few hotspots. Yeah, so that is why we later grounded the upper and lower die edges grounded in with 2.5 millimeters, and then see 300% improvement. That's significant help. Yeah, so some lesson learned we did build up in the past.
Okay.
But details I probably can ask our tool managers to give more technical answers. Yeah.
A question regarding the radius to thickness ratio that you had mentioned, Alex, of greater than or equal to 5T. The question is there a plan of making this a standard within the OEMs?
No. Yeah, this is like the minimum recommendation that we have, considering the relation R&T, and of course that as smooth we can design the part is better for third gen products. This is the minimum recommendation, but of course that if we can put a radius above 5, it's better for the product.
Oh, okay. So it's a recommended one. If you want to go tighter, you need some specific development in order to get there, right?
Yes, correct.
Okay. What is the typical gauge thickness range for these Gen 3 steels?
Yeah, we can figure out this through our website, or you can reach me out and then I can check precisely.
Okay. Very good. Okay, this one is for Cheng, and I think it probably warrants a communication directly with Cheng, because it says, what insights can suppliers share about their experience using Gen 3 steel grades in production? So I think this is kind of really a detailed question. So I would recommend contacting Cheng directly if you don't mind.
Okay, no problem.
As a general comment, let me go to this question. Any thoughts on new failure criteria instead of conventional FLC diagram for third generation steel? So in other words, we have the forming limit charts. Do you think that something different is in the works for Gen 3 steels?
Oh, I recommend that to have in mind that FLC, the standard FLC defined for third gen product, when we have the second form, the graph change, and then we have a new FLC diagram for second operation. Then we must have this in mind to avoid problems and do the simulation, virtual simulation to control it.
Okay.
Okay.
All right, Cheng, question for you. It's regarding the GM B pillar execution. You went to 1180, with the upper being uncoated and the lower being coated. The question here is which, what material did it migrate to or from, I should say? What was the original grade and that migrated to this Gen 3? And has this been implemented elsewhere?
We see the different for B plus. We see different materials used. For this one, I haven't checked back to the GM design, but we have for B plus, we have the hot forming part and cold forming part. We see 1180s. A majority will be using this. And then sometiime we using the hot forming in Europe, using hot forming, and then some we using the clutch. Depends.
Yeah. Well, do you think they migrated from a dual phase grade to the Gen 3?
That's what I
okay.
predicted. Yeah.
Okay. Very good. Any other applications for Gen 3? This again is an open question for both of you. Any other applications other than the B pillar?
Alex, you want to take this question? I think you see more
OEM.
Yep.
Basically, I recommend the Gen 3 grades for structural parts. And we can work to check which type of grades fit better for each kind of application. And then we can recommend for these parts that I put in the chart that I showed. And also for some hoof cross members, I think that this grade can be applied as well.
Yeah, we also in the other application, we see some trend is on the bumper side, go to 1470 to be also there.
Okay. And it's possible to explore also using the whole forming process.
Okay, well, thank you so much, both Alex and Cheng. This has been very informative. It's a very nice, comprehensive overview. And again, my apologies to all the participants. We have a lot of questions. If we didn't get to your question, kindly contact Cheng or Alex directly at the emails that you see on your screen right now. And with that, back to Brian.
All right, thank you again, Alex and Cheng. What a great topic, very important topic, obviously. And with all those questions, we could have gone on for another 30 or 40 minutes, I'm sure. But thank you for joining us, Hisham. As always, thank you for fielding the questions. And if your question didn't get addressed, as Hisham said, emails are here on the screen. Also, just as a reminder, our recording and copy of the presentation will be available on our websites in the week ahead. It will take us a couple days to get them there. And once again, if you haven't already done so, registration for the annual Great Designs in Steel Technology Symposium taking place May 20th in Novi, Michigan is open. Visit greatdesignsinsteel.com to register. And in the meantime, we hope to see you there. Make it a great day.